shortly after 11. We'll just let people to trickle in for 1 or 2 minutes, and then we're gonna get started. Okay, I think it's time for us to get started. Welcome everyone to the new and the next webinar of Blazing SQL. We are GPU Accelerated SQL Engine, and this is Introduction to Distributed Computing. Joining us today is Jacob Tomlinson from NVIDIA, who is our Dask whiz, who will walk you through the content that he's prepared introducing Dask. But before we get to that, let me very quickly introduce you to our platform and to Blazing SQL. Blazing SQL is a SQL engine that runs on GPU data frames. In this particular example, we simply read a CSV file into a data frame, cuDF data frame, and we can quickly create a table on top of that data frame and run any SQL queries that you pretty much like. In this particular case, we just simply counting how many rows there is in the taxi table, but those possibilities do not stop there. Blazing SQL is part of this greater Rapids ecosystem. We've already talked about Rapids in the previous webinars when we introduced cuDF data frame. And we also had Blazing SQL, Introduction to Blazing SQL, the distributed SQL engine in the past webinars. If you haven't seen them, you can go back to our YouTube channel and then watch those recorded webinars on demand. And today, as I mentioned earlier, Jacob is going to introduce Dask and the Dask to us. This Dask is a library that allows you to scale your computations from a single machine to multiple machines. Dask scales both the CPU computations and GPU. And today, he's going to show us how to scale your GPU computations to using Dask. Very quickly, Blazing SQL stack. Most of the time, you will be interacting with Python. What we do underneath the hood, we use Cython and JPipe to call Apache Calcite that creates relational algebra. And that relational algebra engine from Blazing SQL takes on and then runs a CUDA kernels underneath the hood. Dask helps us to take that stack and distribute that across clusters of hundreds of machines. We've run successfully on clusters that were upwards of 700 GPUs at a time. In terms of the Rapids ecosystem, where does Blazing SQL sits? Blazing SQL, just like cuDF, sits at the very beginning. So when you prepare the data, when you do data featureization, Blazing SQL and cuDF go hand in hand. Actually, Blazing SQL, whenever you run a Blazing SQL query, it returns a cuDF. So we can switch back and forth between Blazing SQL and cuDF to do all the data processing you need in order to hand it over to cuML or cuGraph. On top of that, Dask allows you to take all of these computations and run them in parallel in a distributed way. What enables all of this interchangeability is Apache Arrow, that the GPU memory representation that allows us to move the data, well, actually not move the data stays where it is, but read the data and then manipulate the memory objects right as they are without necessity of constantly converting and copying the data between, even in memory, saving us time and then giving us that benefit of additional speed. So how does it work? If you run Blazing SQL, you effectively import Blazing contexts and create a Blazing context from over there. You can register the data. So the data can be sitting in a Blazing SQL, in a S3 bucket on AWS. So it can be remote, or the data can be local to your machine, and then you can create table directly from a file that is local or remote to your machine. Or if you already have a cuDF or Dask cuDF, you can create a table on top of that. When you use Blazing Context and you want to scale up your computations to multiple machines using Dask, you can pass a Dask client to the Blazing Context when you create it, and all the computations will then scale automatically. So once you read the data, it can be pretty much in any format that Rapid supports, so CSV, Parquet, Org, Pandas, cuDF, whatnot. You normally would do your feature engineering, so Blazing SQL or cuDF interchangeably. I use them interchangeably. Whatever is easier for me to do in one framework or the other one, I use it then. And then once you're happy with the results, you can pass it on to machine learning. In this particular case, we present XGBoost, but cuML, that is part of Rapids, has plenty of machine learning algorithms that allow you to build pretty much any machine learning models. If you want to use and massage your data to hand it over to any deep learning framework, there's also ways of doing that. Rapid supports TensorFlow, PyTorch via the DLPack memory representation. So how do you get started with Blazing SQL and Rapids? Well, there's a couple of ways you can do this. Today, we're going to use appblazingsql.com, but you can also go and download a Docker container or install the Blazing SQL via Conda. We are right now part of Rapids, so whenever you download Rapids, you automatically have Blazing SQL included. So right now, this is very quick, very dirty introduction to Blazing SQL. But before I hand it over to Jacob, we need to do a couple of things. So I will ask you now to go to appblazingsql.com. I'm already here. I'm going to just restart that. And what we need to do is open a new terminal and actually wipe out the welcome to Blazing SQL notebooks. We do this because we recently pushed the new changes. So we're going to clone a clean repository from GitHub. So we're going to do welcome to Blazing SQL notebooks. We're going to remove that. And then we are going to go to GitHub and clone. Oops. Just going to clone this. I believe we already pasted the links into the chat window. So if you're following us online, you can just go and head and do this. And right now, we should be getting all of the latest notebooks. Before I hand it over to Jacob, I'm just going to double check. This shouldn't take too long. All right, so let's double check webinars, Rapids introductions. There we go, 04. So I'm going to stop sharing my screen. I'm going to invite Jacob right now to take the reins, and I hope you guys enjoy what Jacob has prepared for you.
Great, thanks, Tom. Let me share my screen.
Go for it.
Okay, so you should be able to see my notebook and everything. Please shout if you can't. I've just followed Tom's instructions. Obviously, I wrote this notebook, but I've deleted my Welcome to Blazing SQL notebooks and headed in here and opened up a fresh copy of the notebook. So make sure you open that up. Also, what I've done here is there's another tab, is 3 down on my JupyterLab. This is the MV dashboard, right? This gives you some plots that show you the usage of the GPU on your system. I've opened up a couple of those. I've opened up utilization, memory, and GPU resources. That's these tabs over here on the right. This is just so we can kind of see what the GPUs are doing. So what I'm going to talk you through is Dask. We're going to touch on some aspects of Rapids, and we're going to use some of the Rapids internals as we go through. But what I've done here is I've taken like what we generally deliver is like a 90-minute tutorial on how to use Dask and like all the different aspects of it. And I've tried to kind of condense that down and make it specific to Rapids and Blazing here. So yeah, just to reintroduce myself, my name is Jacob Tomlinson. I'm a software engineer at NVIDIA. I spend my day contributing to the Rapids open source projects, and I'm a Dask maintainer. So I look after a few of the Dask sub-projects, particularly targeted around deployment of Dask onto various clusters. But kind of I help out in all aspects of Dask. So as Tom said, Dask is a set of tools that help you scale out your Python workflows onto multiple machines, but also just like multiple cores in a single machine, or multiple GPUs in a workstation or server, right? So in my laptop I've got like a processor with 12 cores. Typically Python is like a single threaded application. I'm kind of limited to often using one core unless I'm using some library that can do stuff kind of below the Python level. Also, I have a data science workstation that has 2 GPUs in, and Dask allows me to make use of both of those GPUs when I'm doing Rapids operations. And it does that by breaking up your workflow into a task graph, right? So as you write your Python code, Dask is kind of building up this graph of all the operations that it needs to execute in order to run all the way through that code. And by doing that before actually running the computation, it allows you to then run different bits of that graph on different machines in different places, on multiple GPUs, on whatever. So there's some kind of stuff here. I'm not going to read through kind of everything in this notebook. It's quite a long one. It's in the repo if you want to kind of track through this in your own time. But Dask is here to try and make your life a lot easier in terms of scaling things out. So first thing I'm going to do is I'm going to run this big gnarly cell here, which is just going to do a bunch of stuff that you don't really need to worry about. I'm just setting some default config and downloading some data that we're going to use in this notebook. There's not a huge amount of stuff. I just didn't want to kind of bundle it up into the Git repo. So once that's run, that ran pretty quickly for me. I just want to make sure I've got a data directory popped up over in my viewer on the side with a couple of little data sets in it. I'm not going to be pushing this particularly hard. I kind of want to convey the concepts of Dask more than kind of show large scaling here, because then you can all kind of follow along with what I'm working on. So Dask covers a variety of different data models, same as Rapids does. And the 2 main things we're going to talk about here is data frame workflows and array workflows. So if you're used to writing stuff in Python, that would be a pandas workflow and a NumPy workflow. Now in Rapids, we have cuDF and CuPy, which are like GPU accelerated versions of those libraries. They follow the same API, and they do the same kind of thing. It's just that the back end of those libraries have been written to run on the GPU instead of the CPU. Dask does exactly the same thing. So we have Dask data frame and Dask array, which both follow the same APIs as pandas and NumPy. And because Rapids follows the same APIs as pandas and NumPy, and Dask follows the same APIs as pandas and NumPy, we can use the 2 together. Everything's kind of interchangeable here. A lot of the work that we do in Rapids at NVIDIA and as part of the community is to engage with these open source projects and make all these things play nicely together. So in order to make use of multiple GPUs, multiple machines, one of the other nice benefits that we get is we can deal with larger than memory problems. So if you're typically working in QDF or pandas or something, you're limited by the amount of RAM that you have in your machine. If you have a big CSV file or a bunch of CSV files that's a couple of terabytes, you can't load that all at the same time, right? Dask handles that by chunking it up for you. So I've got a little image here that kind of shows an overall Dask data frame is a table of data, but it's made up of smaller pieces inside. So on a CPU, it's made up of pandas data frames. On a GPU, it's made up of QDF data frames. But it allows Dask to kind of shuffle these in and out of memory, swap stuff to disk, and shuffle things between nodes as well, depending on how memory works. So let's start running some code, and you can see what I'm talking about. This very first cell here is going to be setting up our Dask cluster. I'm not going to go too much into that now. There's a section on that towards the end. But what I'm going to do is I'm going to run this, and you should see this kind of client output pop up. And you can see we've got one worker here. It's because one GPU has been detected on app.blazing SQL, and that GPU has got 16 gig of RAM. Now that we've got our cluster launched, our cluster of one, right, but it's still a cluster, we're still using the same kind of workflow. We connect a client to it. This is what tells Dask where work needs to be submitted to. You just have to create this client object in the Python scope in Python namespace. Once that object exists, we can carry on with our Dask work, and everything will be running on this cluster. You probably saw my GPU memory increase slightly then as well, just as things kind of got initialized and provisioned. So the next cell I'm going to run is using Dask QDF to read in a CSV file. Now this is almost exactly the same as doing like a pandas read CSV or a QDF read CSV, but we're using Dask QDF, right? This package comes installed as part of Rapids, and it kind of bridges you between Dask and QDF. So the API is the same. You do the same calls, but there's a few extra arguments. One of the arguments we have here is the block size. So we're setting a block size here to say, read in this CSV, but just read it in chunks of this size into separate partitions. Now I've gone with pretty small data here, so I don't think we're going to see like a huge amount of partitions here. There might just be one. Yeah, there's just one chunk here, right? But if this is like a, multi-terabyte CSV, or maybe you've got many and you put some kind of string in like that to load many CSV files, it's going to read that in chunks and handle your memory management for you. So by just outputting the Dask data frame object here, you can see the representation. If you're familiar with pandas or QDF, this looks similar to a data frame from pandas or QDF, but there's no data in here, right? We've just kind of got, here's my column names, here's the D type of each column, but there's no data in here. That's because Dask is doing everything, lazily, right? It's doing everything just in time. So we've said, Dask, please read this CSV file. What it's actually done is it's just had a peek into the top of the CSV file to say, what are your columns? What are your data types? But it's not read the whole thing yet at this point. It's just kind of worked out what would I need to do in order to read that file. So it's created this representation of the file with correct metadata, but no data yet, which is why our GPU usage is not particularly high. GPU memory usage is not particularly high here. But we've created this kind of abstract representation of our data. Now we can do some different operations on it, right? We can do something like, let's have a look at what the type of each of our partition is. We have this handy method on a Dask data frame called map partitions, where you say apply this function to each of my individual partitions, and it will kind of load them one at a time, run your function, and then give you the result. And we're going to explicitly say here compute. This is how we go from saying, load my CSV file, and Dask says, yeah, I've loaded it, but I haven't actually. By saying .compute, we're saying, actually, no, Dask, now is the time to realize the graph, right? You now need to work through the graph because I want the result of that. So we're just going to call type on our partitions just to see what's inside our data frame. So if I run this, you should see my GPU start to do something, and then we can see it's come back. We've only got one partition, and it's saying that the internal data type of that partition is a QDF data frame, right? If I'd loaded this in with Dask data frame, it would be a pandas data frame. Now there's a couple of exceptions to the rule of having to call .compute to make Dask do things. One of those is doing a length on anything. Dask will assume you actually want that. And the other one is doing head. So if we do a head on our data frame, this will actually start to read into that first partition and get us some actual data back. So this is just like doing a head in pandas or QDF, but we can now see into our data frame. And we can see some information, right? This is an example data set. I think it came from, you know, the Kaggle open data sets or whatever. You can see this is beer reviews. I think there's kind of review information about different breweries and different beer styles. And we can do pretty standard data frame operations on this, right? We can see if a beer style name contains the phrase IPA and then filter down our data frame by that and just have a look at the top entries within our data frame, right? This is showing us our IPA beers. This is pretty standard workflow that you would do in pandas or QDF, but we're doing it in a distributed, lazy fashion, right? We can assign our data frame, you know, kind of filtering our data frame. So if we want to actually extract a new data frame, which is just our IPA beers, we can do that. And then we can do, you know, maybe like a group by and work out what the, you know, best reviewed beers are within that. We get our mean IPA review object, and we can have a look at this, right? This is another data frame, and it looks the same as our representation before, right? It knows what the structure is. It knows that there's one partition and that it's going to have these column names, but it hasn't worked out what the actual results are yet. It's just given us a representation. But it's showing us here that this data frame will take, there will be 7 tasks that need to be calculated on the task graph in order to work out what this data frame looks like. And I can call compute on this to you know, explicitly look into our beers and see which ones have the best reviews. Now this is kind of showing us everything back in Jupyter. We're able to see into these data frames because everything kind of gets converted all the way back to a pandas data frame at the very last second in order for you to kind of see the nice HTML representation in Jupyter and have a look at it. Now you can do other things that you would expect to do in pandas and QDF, like write this new data frame to disk. But because Dask works in this kind of partitioned and chunked way, if say we had a data frame of 100 partitions, if we want to write that to disk, it's like a non-trivial thing, right? You don't want 100 different tasks all trying to write to the same file. So what we do when we say, you know, to CSV or to JSON or whatever, you can actually give it wildcards like you would when loading data. You can give a wildcard to say, write this out to many CSV files. I think, you know, this was a small example. So this is just written out one CSV file called IPA0 on here. But hopefully you get the gist, right? This would allow you to, in a distributed fashion, write your data back to disk. So let's move on to like another example, hopefully to kind of show you some more standard core data frame functionality that's being run in a chunked fashion with Dask. What I'm going to do before that is I'm actually going to call client restart. I'm going to do this a couple of times as we go through this notebook, just to kind of clear out any stuff that the Dask cluster might have in memory and reset some of my futures and things. We'll get onto kind of that as we go. So instead of reading our beer data, let's read this other data set that we have called page views small. This is I think Wikipedia page view data, right? So kind of analytics data that you might want to look into if you're running a website like Wikipedia. And we're going to say, please read this file in. We're going to read it in chunks of 100 megabytes. Again, this is only loaded in one partition. There's only one chunk because the whole data set is less than 100 megabytes. But if you're working with larger data sets, this would read in more partitions. I could change this number. I could make this smaller, right? But we don't want to give our GPUs too little data. Otherwise, we're not going to get the performance benefits that you get from parallelizing your operations on a GPU. But I'm going to read in exactly the same as I would in you know, any data frame tool. Read CSV. I'm explicitly going to say this is a space separated file, and I'm going to read it in chunks of 100 meg. So we get another data frame. Again, same layout as we saw before, but we're going to kind of, you know, give it some more information now. So let's set the column names. Let's drop one of the unnecessary columns that we don't actually want from here and get ourselves a new data frame. So this is going to show us the project. This is the language of the Wikipedia, right? Wikipedia is split out into separate language-based subprojects. And we're going to see which page, each row is a page and the number of requests it's seen. So we can also do more filtering, right? We can say, I just want the English Wikipedia data. So let's make another data frame called DDF3. And you can see each time I run this, right? We started with one task to read a CSV file, then 3 tasks to change our column names and drop a column. Now we're on to 6 tasks to do some filtering and subsetting. And as we're kind of generating this graph of operations we want to run, we can now kind of tell Dask to do those things, right? These cells ran immediately, but now we need to say, actually, no, it's time to do some work. We want to see some answers. So let's say we want to see the count of how many pages were accessed in all of Wikipedia versus the English Wikipedia. And so if I run this, you should see my GPU memory starts filling up, my GPU start being utilized, and we can see our counts. I run it on English. You can see our counts come back for that as well. I could also do this in a different kind of operation by using a group by and checking whether the project is in a list of various other languages. Say we want to see, what is the count for English, French, Chinese, and Polish. I can run this and it will kind of show me a broken down view, right? It's the same as any kind of data frame operation you might be used to, but we've got this abstraction in there, right? We've got Dask in there, it's abstracting this for us, it's building these task graphs and it's executing them for us, which allows us to then leverage larger than memory data sets and multiple machines in order to run through this. Now, everything we've seen up until this point, we've just kind of been running through a notebook. We've been looking at this MV dashboard, so we can kind of see the GPU utilization and memory and things going on over on the side. But Dask has its own dashboard as well, with a whole load of information about what's going on. So if I actually restart my client again, we will see our client representation printed out as we have already. But one of the things in here is a link to a dashboard, and this is kind of linking through to the Dask web page that's being run by Dask for us and collecting a bunch of information. So this has got information about how much data is in memory, how many tasks are being processed by the cluster. We can see a stream and progress bars and things when we run stuff. We can click over to the workers tab. We can see, we've got our one worker here. It's got, this much memory being currently used of our 16 gig of GPU memory. We can see how much CPU is being used as well. We can have a poke into tasks to see our task stream and get back all sorts of information about the cluster and how it's running. We have a GPU tab here, which is a recent addition. You can see this is the same as these plots here, right? GPU utilization and GPU memory, but this is for all of the GPUs in your cluster. So if you're running on, a 700 GPU cluster, like Tom mentioned at the beginning, this would have 700 bars for all of the utilization. So you can get a good insight into how your resources are being utilized. In our notebook, we could kind of run through those same operations again, read in our data, drop the column and count it and compute it. And if I head over to the dashboard, that all happened extremely quickly, but we had some progress bars appear to show what was being run, and we can see our task being executed here. I think our task has actually been collapsed down into one task. Dask does a whole bunch of like graph pruning and fusing of tasks to give you good performance. We can head over to the profile tab here, which gives you a flame plot of what happened, right? So all of the plots we've seen so far are kind of real-time plots showing you what's happening on the cluster. But the profile plot is kind of showing you some historical data about what was the last thing that I did and how did all those function calls break down. So at the bottom row, we can see our task that was submitted that took the full length of time. That task was broken into a read CSV section and then a data reduction. You can kind of hover over these and head up to see which functions within my call took all this time. It looks like there's only a couple of function calls here really that ran, but in a more complex example, you can start seeing where are the bottlenecks in my code, where's the performance happening. And this is all kind of free and out of the box, right? We're just using Dask cuDF instead of cuDF. All our calls are exactly the same. We're just having to remember to compute things in order to make Dask do them, but then we get all this kind of useful profiling information because Dask has run through this big task graph for us. So I'm going to leave data frames there and kind of switch topics over onto arrays now. So if your workload is more of like a NumPy array, multi-dimensional array based problem rather than a data frame based problem, maybe you use NumPy or CuPy to operate on those kind of things. You can use Dask Array within that suite of tools. And it does the same kind of thing, right? Instead of having a data frame that's broken into partitions, right? And you're only breaking on a row-based, in a row-based way, Dask Array will break in like ad hoc chunk kind of way. You can specify how your chunking is, because NumPy can, support arrays of however many different dimensions and things. So you can kind of specify, I want my chunking to look like this. I want chunks of this size and this shape to kind of hold my whole array. But like you can see in this image, if you had a 2D array, you would have a Dask array, which represents your full data set. And then within that, you would either have NumPy arrays or CuPy arrays. There are also other libraries that kind of build on a level above this. There's a tool called Xarray, which is particularly useful for looking at geospatial data. And maybe the data representation inside that is CuPy with Pint, right, which is a unit-aware array representation. So you can do unit conversions. So you have temperature data that's stored in Kelvin and you want to view it in Celsius or whatever. More intelligence can be added to the array representations, and Dask can just work with those as long as they follow the NumPy format. You're all good. So yeah, Dask arrays are chunked in whichever dimensions you have, and it follows the NumPy array. And the idea is to be a drop-in replacement for these existing libraries to complement them and allow you to do the same things, working out of memory, out of core, multiple machines. So let's restart our client again, just to kind of clear out anything that I might have floating around. Now let's have a look at CuPy and Dask array, and just to see kind of the differences between kind of a bare array and then an array that's been wrapped in Dask. So I can do, CuPy.arrange to create myself an array of numbers. This is just a one-dimensional array of numbers, same as you would in NumPy. I'm just doing it here with CuPy so that it's running on the GPU. With Dask, I can do exactly the same thing. I say I want to arrange with the same argument so that I would get the same array, but I can specify a couple of things here, right? I'm going to say I want there to be 5 chunks. I think this is, I sometimes forget which way around this goes. This means I want chunks of 5. Yeah, I want chunks of 5. So I'm going to ask for, 17 objects or whatever, 17 elements in my array, and there should be, 3 chunks of 5 and a chunk of 2. And then I'm also going to use this is a kind of a new feature that's come into Dask and NumPy recently, which allows you to give it a like option. So by default, if I didn't have this here, this would give me a NumPy backed Dask array, right? It would create a Dask array and the internal objects would be NumPy arrays. But I can say, no, I want your internal objects to be like this other object that follows the same format. So I'm just going to give it an empty CuPy array and say, please make your internal representation like this other array representation here. So I run this, we can see our array printed out. We have a nice representation here. This is different to kind of what we had before because we don't have column names and we don't have that kind of thing. So what we have instead is just some information, some metadata about the array, and also a visual representation in Jupyter of how that array looks. So we can see, well, this array is 136 bytes. Each chunk of that array is 40 bytes. The overall shape of the array is one-dimensional, and that dimension is 17 elements long. And each chunk is one-dimensional and 5 elements long. So in order to cover my whole array, I have 4 chunks. Each of these chunks is an int64, and the internal representation is this CuPy array, right? So we can see here that saying like an empty CuPy array has resulted in me having a CuPy array representation. We can also have a look at things like, what's the, outside of Jupyter within your other workflow. You can see the dtype and the shape of your array. You can say, this is an int64, it's a 17 long array overall. But we can have a look and say, well, how many chunks are there and what's the chunk size? So this will give us a tuple representation showing these are the chunks. There's a chunk of 5, a chunk of 5, a chunk of 5, and a chunk of 2. And our chunk size is 5s. Although, if we don't divide perfectly by 5, we'll have a little chunk on the end. We can then do kind of standard operations, whatever you would do in NumPy and CuPy. So we could square all the numbers in our array. What this will give us, I'm not assigning this to anything, right? I'm just saying, take my Dask array and square it. That returned immediately. That's because, as Dask did previously, it's doing this lazily. It's just working out, if I were to square the things in this array, what would I do? So like the output array is the same shape and size as before, because we're just changing the values. But instead of having 4 tasks, we now have 8 tasks, because we have to square each chunk. So we're kind of building up this graph again. And I can explicitly say, no, I want to compute that. Let me see the squares of those numbers. And it'll print out our new array. And you may have seen the GPU kind of flicker with a bit of usage there. We can also have a look at the type. Now, when we call compute in Dask array, it's trying to give it back to us kind of directly as it is. And it's showing us that this is a NumPy array, right? So we're kind of going from this distributed CuPy arrays represented as a Dask array. And then when we do this operation and pull it back into our notebook, it gives us the result back out in a NumPy array format. Now, Dask array follows kind of all the standard operations you would want to do in NumPy. You know, you can do regular Python things like sum and mean. You can do slicing and all that kind of stuff. It follows the same thing, because we're using the internal protocols that NumPy is kind of laid out, right? So there's this API for building things that are like NumPy. Now let's do some other operations here, right? So Dask array is implemented using blocked algorithms, which allows us to break up our computation into smaller pieces. So say we want to generate a giant random array, right? In order to generate a giant random array, we need to generate lots of small random arrays, right? That's how Dask would think of this. We want lots of chunks, and we want those chunks to contain random data. So what we're going to do is we're going to set up a new kind of random state class. This is kind of under the hood. You often don't see this part of you know, calling random.random or something. But we explicitly want to create a new random state class and say, please use CuPy's internal random state in order to generate this random data. So instead of creating a NumPy array on main memory, we're going to create random CuPy arrays with the GPU on GPU memory. So this RS object here is kind of equivalent to, you know, numpy.random. Now we can do all the kind of standard calls you would do on numpy.random. So if we wanted to do numpy.random.random and say, you know, I want 20 elements in chunks of 5, we can do that, right? And it gives us another array representation that's showing, you know, this is a similar shape and size to what we had before, but this is made up of 4 tasks. Instead of initializing the data with the data we provided, it's going to initialize these arrays with CuPy.random, right, internally. And we could do something like let's sum all the elements in this array. But we haven't said compute, remember. So we're going to say result equals the sum of all the elements in this array, but this is going to give us back another representation, right? This is another Dask graph here. And now this is actually a singleton. This is a single element, right? A single number, because it's the sum of all the items in this array. So the way that Dask shows you that is it doesn't have a shape or a chunk size or anything like that. It's just an 8-byte float 64 number, right? But it's showing that there are 9 tasks in order to get to this point, and we can call .compute on there to get that number. So you know, under the hood here, the GPU, I think if we head back to the dashboard, yeah, there's not a huge amount to see kind of going on here, because these are very small operations, but you can see that was probably generating a random array and that was summing it. These are our small tasks working in here. And I think if I head to the profile, we can probably see, yeah, in here, we've got our random sample function call here. And then we've got some summing going on in, yeah, summing going on in here. And then this is probably, oh, there'll be a couple of sums going on, right? If you call sum on a chunked array like this, it will call sum on each individual array and then bring all of those answers together and call sum on all of those. So you'll get like a MapReduce style sum going on there. I can also kind of set different chunk sizes. So instead of having a 1D array, we'll have a 2D array that's 15 by 15, but we're going to specify a chunk size of 10 and 5. So we're going to get some 10 and 5 chunks, and then we'll get some kind of 5 and 5 chunks along the edge here. And we could do something a bit more complex here. Let's add that to its transpose and then call sum on that to get like a bit more interesting graph going on here, right? This is now a 65 task graph. And if we call compute on this, that probably ran extremely fast as well. But let's refresh and have a look. This is going to be, you know, pretty similar to what we had before here. So that's kind of a quick dip into Dask Array. Just to kind of recap, that follows the same API as NumPy. We're using CuPy for the internals here to get the GPU acceleration, but Dask is allowing us to distribute onto multiple GPUs, multiple machines by creating these clusters. So there's a couple more things I wanted to cover. One is kind of diving a little bit more under the hood into how Dask works. And then I kind of want to touch on cluster managers. Can I just check, Tom, how are we doing for time?
We good. I think we still have probably around 15 minutes. You can perfectly cover.
Okay, that's perfect. Okay, so let's kind of what we've done so far is we've had a look at two high-level API implementations, right? The data frame API and the array API. These are things that have been built within Dask to mimic these other libraries and make use of other libraries like NumPy and CuPy and Pandas and QDF and all that. But these are kind of high-level abstractions built for specific use cases and specific purposes. But what we can, let's just take a minute. We're going to step away from kind of GPU everything for a minute, and we'll just have a look at what's Dask doing, how does Dask work, and kind of how does this happen inside. So we kind of talk about two different things here. We're going to talk about delayed functions, and we're going to talk about futures. So let's start with delayed functions. Say we have some regular old Python functions here, right? We're going to have an increment function, which takes a number and adds one to it. We'll have a double function, which takes a number and doubles it. And we'll have an add function, which takes two numbers and adds them together. Right, these are very basic functions, but we've just injected a little half-second sleep inside each one, just to kind of pretend that these are slightly harder functions than they appear, right? There's something that's going to take your machine a little while to do. So if I define these functions, let's make use of them to do something. So let's take some data, the numbers 1, 2, 3, 4. Let's also take an output array that we're going to put some answers in, and we'll iterate over the data. And for each thing, we will add 1 to the number. We'll then also separately double that number, and then we'll add those two things together, and then we'll append that to the output array. So we'll build up this array with 4 elements in, and those elements will be, 1 plus 1 and 1 times 2, both added together. And then the last thing we're going to do is we're going to do a sum of all of those elements, right? So we're going to go through a few different steps here. And if we've got a time magic here in our cell. So I run this, it's going to time those function calls, and we'll see how long this takes to run through. So that took 6 seconds, which is what you'd expect, right? Because these are each a half-second operation. So we have 4 elements here, and we're doing 3 operations on each of those elements. So times all that together, you'll get 6 seconds of sequential calculation time. But what we can do instead of calling these functions is we can make them delayed functions. And this is how Dask works internally, is we make this a Dask like lazy representation of this function. And we can do this with a decorator called delayed. So we can do from Dask import delayed, and then we can call, we can either call delayed and pass it a function, or we can use it, I think further down we use it as a decorator here, right? We're going to redefine the functions in a bit, but we're going to create a new version of the increment function called lazy inc, and that's going to be a delayed version of that function. So if we run this, we now have lazy inc, and say we want to call that function, we can do that. We can call lazy inc, and we can give it the number 3. And what this will give us is this delayed object. Right? This is you've called this function, and Dask is saying, I appreciate you've called the function. Here's a delayed representation of that function. Here's the ID of the result of this function call. Come back later and I'll have done it for you. We can visualize these graphs. Now, sadly, I don't think Graphviz was working properly on this platform, so I can't show you the graph representations, but feel free to kind of have to prod around with calling visualize on these graphs on your own machine. But let's call compute on here. We can see that doing lazy inc on this number 3 gives us 4, which you'd expect, it's inc. But we explicitly call compute, right? This is what we were seeing before with calling stuff with Dask data frame and Dask array. But we've written our own function here, right? Our own function inc, we've turned into a delayed Dask function, and then we've computed it using Dask, right? And this is how everything's built in Dask, is using this model. Now we can, we could double that again by running, lazy ink again on our output, and this is going to build up 2 steps on our graph, right? So we're going to have our input number, we're going to have one lazy ink that we're going to call, and then we'll have a second lazy ink, right? So we have this kind of 3-point graph here, which we would see or visualize. And if I compute that, we should see number 5, right? Because we've incremented 3 twice now. Now we can use this to kind of build a bigger operation, right? The kind of convoluted example I ran through a second ago is building up a graph of what's happening. So let's redefine all of our functions rather than doing what we did a second ago. Let's redefine our functions exactly the same, but we're going to decorate them with @delayed. So we've now got our lazy Dask functions, and we're going to do exactly the same thing here. We're going to take our data, we're going to have our output array, we're going to iterate over them, we're going to do inc and double and add on our data, same as before. The only difference in this cell here is that we're actually going to call delayed on Python's built-in sum, right? We're going to make sum lazy as well, even though this is a built-in Python function. And then we're going to get total. So if I run this, this didn't take the 6 seconds that it took before. It now took, 1 millisecond. And that's because it didn't do anything, right? Dask hasn't done anything here. It's just created the graph representation of what would this look like. So we'd have our 4 numbers across the bottom, and we would increment them, and we would have another 4 numbers, and we would double those, and then our graphs would come together, and then they would kind of come back together into a big sum at the end. And we can call compute on this, and we'll time this now, right? So before this took 6 seconds. What we're going to do here is we're going to time this, and that also took 6 seconds. And I haven't thought about this because I normally run this tutorial on a machine with 2 Dask workers, 2 GPUs. So it should take 3 seconds, right? So sorry about that. I didn't think that through. But if we had 2 GPUs on this machine, or we had a Dask cluster with more than 1 worker, the tasks that could have been run in parallel, because a lot of these taking in 1 and incrementing it, and taking in 2 and incrementing it, are like completely independent operations, and they don't depend on each other in any way. So Dask can run those concurrently if it's got additional workers to do that. So depending on how parallel your algorithm is, I think this algorithm can parallelize. You could have 4 workers running on this, and it would go roughly 4 times faster. Obviously, the aggregations towards the end have to kind of come together. But this would, you could parallelize this out onto 4 workers, and it would take much less time. And so the only difference between what we did initially, we defined our functions before and ran a cell that looked a lot like this, and it took 6 seconds. Now we're decorating our functions with delayed and explicitly calling compute. And if it's possible to parallelize our algorithm, our graph, it will do. And that's how we're able to move stuff. Now, Dask also has this idea of futures, right? This is built on top of Python's kind of own internal concurrent futures. And these futures are kind of these representations of the output, right? So we have a future here, a future ID of this sum, this like long ID here. But it can use that to track all the individual pieces of the graph. It can use it to avoid duplication. And it also can use that to move memory around between different machines, right? So Dask can know, oh, I can start working on this over on this machine, and I can work on this part of the graph over on this machine. But at this point, there's a common key that's needed. So I'm going to, calculate over here, and then I'm going to have to copy some memory from here to here in order to calculate this common key within my graph. And it does that using the futures interface. So let's have another function call. We'll define increment. It's going to randomly sleep this one. And this one, we're going to specifically give this to Dask and say, run this for me. This is, this isn't a delayed function. I just want you to run this function for me. It's slightly different to how we've kind of run things so far, but we're going to do client.submit. We're going to say, here's this increment, and here's 7.2, and I want you to run this function for me. By doing that, it's going to give us back a future, and we can see that this future is pending. So Dask is doing it. This is kind of like saying compute, but we're not waiting for the answer to come back. But it's saying, okay, here's a future. F is a future, and its key is this, and we can see that it is of type distributed client future. Now, like, time has passed. I just kind of explained to you what that was. And in that time, Dask is probably finished because this is a very small operation. So if I now print the future again, we can see the status has changed to finished, right? It's not pending anymore. It's now finished. It also knows more about it. So we can see that it has a type of a float. And we can grab the result from that future. We can see, yes, incrementing 7.2 is 8.2. We can also delete that future. Now, this future exists on the cluster. So I think if I head back to the dashboard, we can see we have this progress bar of running ink. But like, this future still exists. This future is in our Python namespace. So Dask is remembering that. It's holding on to that because we might call result again, and it will need to give this back to us from our Dask cluster. So we have this kind of increment hanging in memory here. And we can explicitly delete that as you would a Python variable, and that will release that from the cluster, right? So that progress bar is now gone from in here. So we can do the same kind of thing on many numbers. So we can, take a range and increment a range of numbers. So we get a whole list of futures. We can see those, some of those are running, some of those are still pending. I might actually run that again and head back to the dashboard. Oh no, I'm just going to delete futures again and then create it again and head to the dashboard, and you should see, it's remembering it too well. Okay, we would have seen that progress bar loading. Anyway, we have our futures, they're all finished now. And we can get all of the results back in one go using client.gather, right? So this is kind of common in many asynchronous programming paradigms, especially within Python, using gather to gather a load of kind of futures back together. So we can do results equals gathering our futures. And if you have a look at the results, this is all the numbers. These are all the results from this list of futures that we had. I'll kind of skip on. So that's a quick peek under the hood of how Dask works, how Dask defers things to the future and parallelizes stuff out. Now, we've already seen Dask data frame and Dask array, 2 implementations of this. There's a bunch of other things you could do. You could use this to implement your own algorithms. If you can think of things that could be parallelized onto many machines, then you can write your own bespoke Dask code. Now I'm specifically thinking about kind of machine learning, statistical operations here. We have a package called DaskML, which is a bunch of very common statistical operations that you would do there. It's following the same paradigm of, we're going to take an existing library that's popular and we're going to re-implement some of its code. So this DaskML follows the API of scikit-learn and has a bunch of stuff like logistic regressions and things implemented from scikit-learn, but it's implemented using these building blocks, expecting things like Dask data frames and Dask arrays, and allows you to distribute machine learning and statistical code. And we also have QML, which is a Rapids flavor of this, which has the kind of GPU acceleration built in as well. So we can parallelize out our machine learning workloads using Dask natively, or if we want to use something like XGBoost or like GBM or something like that, Dask actually has built-in things for using within XGBoost itself and like GBM. They can use Dask and use data that's already on a Dask cluster and already distributed, and kind of like those tools have their own clustering technologies, but Dask can kind of bootstrap that for them and say, look, here's all the data, here's all the workers, here's how you can execute some code, just run your cluster layer on top of mine, and then you go and do whatever you want, and then just give me the answer back at the end. So there's a whole bunch of things here. I highly recommend you go and check out a bunch of these links. I'm not going to dive any deeper into that here, but this is how we're able to implement big scale distributed algorithms using these small building blocks that we've just played around with in pure Python. So the very last section of this notebook that I want to cover is Dask distributed. So all the way through this, we've been using a local CUDA cluster object. This is something I imported from Dask CUDA right at the beginning. We created it. It found our one GPU and was like, right, we've got a Dask cluster of one worker. Now, this is just one of like many implementations of the Dask cluster manager. This is like a familiar module that you'll find throughout a bunch of different projects. The cluster object has kind of some standard things that you can expect to find from any Dask cluster manager. So if you have a look in there, there's a bunch of standard operations, right? How many workers? These things will be auto-detected if you don't set them, but you can say how many threads per worker, how much memory does each worker get? for GPU specifically, can I use NVLink? Can I use InfiniBand and RDMA and other kind of advanced technologies within that? You can kind of configure your cluster when you instantiate this object, and then use that to create your client. And then once we've done that, we can kind of poke around at the cluster and get information back. So one of the most useful things you can do is there's a get logs call that you can make, which will show you, there's no cluster logs here, but the scheduler, what are the logs from the scheduler process, right? This is a separate Python process running on my machine that is acting as the scheduler of all this work. What are the logs from that scheduler and all the workers, right? We've only got one worker, but we can see what are the logs from my worker. So we can see what's going on in our Dask cluster. Now, this isn't particularly helpful in this case because we've just got one worker and both the worker and scheduler are right here in our notebook on our machine. But when you start scaling out onto larger platforms, maybe some HPC system or a cloud system, these are all going to be separate machines, separate VMs, separate jobs in a queue on some batch system. So being able to pull all of their logs together in one place and look at it right in Jupyter is really helpful. We can also grab that dashboard link directly back that we saw in our client object before as well. Now, there's loads of tools out there for deploying Dask. Many of them I maintain. That's kind of one of the things that I do as part of my Dask work. So there's tools for deploying on Kubernetes, on Hadoop systems via Yarn, various cloud platforms. We have support for AWS, Azure, GCP, as well as other less well-known cloud platforms. We also have another library called Dask Job Queue for running Dask clusters on PBS or Slurm or SGE or whatever batch system you use. And these all follow the same API. You import a class and you instantiate it with some config, but instead of creating Python subprocesses in order to run your cluster, maybe it speaks to the AWS API and provisions VMs and then runs Docker containers on those VMs to start the individual components. Or maybe it generates scripts that are then passed to Slurm in order to submit a whole bunch of jobs to Slurm that will bring your cluster together, right? But it's following a standard API that will be familiar and allow you to kind of transition from one tool to another. Now, all these tools are great for you as an individual to launch a Dask cluster on whatever platform you have access to. But if you're kind of thinking about setting up Dask as a team or an organization, institution, you can also use Dask Gateway, which is like a centrally managed server that you run that will then submit these clusters on your behalf, and it allows you to add authentication and monitoring and quotas and all that kind of stuff, right? So you can make sure that folks aren't running riot, launching Dask clusters everywhere. So yeah, if you're interested in any of these, if you use any of these platforms, then check out the links and you can see how to deploy Dask clusters onto those. But all of the workflow, everything we've gone through would be exactly the same with those, right? You create your cluster for Kubernetes, you use kubectl with some GPU config. Instead of local CUDA cluster, you create your client with that kubectl, and then everything's exactly the same, right? Everything we worked through before will just be submitted to Dask. The dashboard's there, like you can see all of these things, and it's distributed out onto your whatever platform you have. We've got a bit of wrap up and best practices here. This is more just for reference. Please have a look through and see all the various bits of Dask, how to kind of keep things from running out of memory and doing all those kind of things. But yeah, I hope this has been a useful overview of Dask, and I hope this has been interesting, and thank you very much for your time.
Thanks, Jacob. This is really good. And I just literally just refer to you as a Dask god, because that's pretty much how it feels to me. Like when you talk about Dask, that's that's how I feel. I'm constantly learning more and more. So now I'm gonna turn into questions. If you guys have any questions, please go ahead. I'm gonna check the Q&A panel. At the moment, I don't see any, but let's see if there, anything trickles in. But I actually have one question for you. That kind of ties to the end of the notebook that you had. What is your biggest gotcha when you deal with Dask? Like, what would you recommend people that try out Dask as a very, very beginners to avoid, doing explicitly?
I think like the most common pitfall that I think you tripped me up tons at the beginning, right, when I was first getting used to Dask, is you're setting up this distributed system where, we were on app.blazing then, and everything was in that environment. I was using the rapid stable Conda environment that's on there. I created a local CUDA cluster, I created a client, all of this was in the same Python environment. So all the same packages are available in all of those places. But like a big stumbling block is when you start expanding beyond that, maybe I'm going to use Dask SSH because I have a bunch of workstations that I have access to and I want to SSH into a bunch of other machines. Maybe they've all got slightly different Conda packages installed in their different environments. Or maybe I'm going to reach out into the cloud and I've got other stuff locally. Like everything's going to fall apart. If you use local packages that aren't on the remote workers within your cluster, you can start seeing some very difficult to track down error messages. There's one error message just called a killed worker exception, which is a really horrible one sometimes to debug. We actually have a whole documentation page that's like, what does killed worker exception mean? And it generally means look at the worker logs and that will tell you what killed it. But it's sometimes a bit tricky, right? When you start moving beyond one machine, actually debugging when things go wrong, it can be a little bit scary because you've got a whole bunch of machines to think about. So yeah, that's why I like to show the get logs function call so you can get logs back from your cluster. And that documentation page is super useful when you're first starting out.
Yeah, I agree. I think that's a great advice because not many people coming from a single threaded, or the custom environment, even on the local machine, spanning beyond that and going to multiple machines that they might have different configurations might be a really tripping point for them. Jacob, once again, thanks very much for joining us. That was great, and I appreciate your time for doing this. I hope you guys have learned from Jacob, how to start with Dask. Once again, you can just download, to start with, you can just go to rapids.ai or blazingsql.com, get a Docker here, or just conda install Rapids package onto your machine, into your Conda environment. And you can get started with that, given that you have a fitting NVIDIA GPU. Thanks again. I appreciate the time, and till next time.